Hey, welcome back. This is going to be a longish episode, so I thank you in advance for your patience. Welcome to Code Space. My name is RK. Ravi is in Bangalore actually, and today let's build a Galton's board. All right, welcome back. So here is what we are going to be doing today. All right, I spoke about something called as a Galton's board. I do have like a very small video to show you, but before that, let's just look at all of the components of a Galton's board. All right, so what's supposed to happen is that all of these balls or these ball bearings are placed in a reservoir here, and then they fall down and they run through this gauntlet of pegs. Now, once they fall down, they are actually collected into these buckets. And when that happens, they automatically form something called as a binomial distribution. Now, this video isn't there to discuss as to why this happens, but we just want to basically simulate it. All right. Before we do that, let's look at what an actual Galton's board looks like. So here you go. So this is basically the setup. You have a reservoir of these ball bearings. Then it falls through this gauntlet of pegs, and it automatically forms this binomial distribution. At least that's what it is called. I'm not entirely sure that what the explanation for binomial distribution is, but we'll get to that at some point in time. But that's how a Galton's board essentially works, and that's what we want to simulate today. All right. So if you've been following us for the last few weeks or something, you would realize that we have some interest in physics and physics simulations and all of those things. And I think overall we are sort of building up to sort of creating our own physics engines, or at least some semblance of a physics engine. I think the interest for that physics engine or building something of a physics engine started with this something called as a soda constructor. When I first began my career, I saw this site. It was written in Java, and it was Java applets essentially, and it allowed you to build these Java robots. These stick robots. These stick robots that you can essentially have them move and everything. The site no longer works. The soda constructor company, whoever designed it, they no longer have the robots or no longer have the site up. But somebody else has built this open constructor thing where you can build your own robots. It used to look exactly like this. So what you could do was you could create hard points, you could create muscles, and you could create bones. And those muscles, you can essentially give something like, movement, or you can have them contract and expand at a very precise rate, and that would create these beautiful motions. All right. Now the Wayback Machine doesn't have all of the Soda Zoo animals, as they were called. So these were designs that were basically provided by all of the people around the world, and there were like so many different types of machines. I remember seeing so many different types of robots and cranes and cars and steam engines and things like that. People had just simulated it out of very simple physics. So this constructor essentially allows you to, generate these robots and everything. So I'm going to link everything in the description. So this was just a little bit of a tangent that we took to the main topic today. But I just wanted to introduce everyone over here to the soda constructor. There is a link over here, that probably allows you to create your own machines like this. So I'll let you actually do that, if that interests you. All right. So getting back to the matter at hand. So what do we have today? All right. All right. Let me just reopen this pack. So there are three components to this Galton's board. Number one is the ball bearings themselves. All right. We're going to call them balls over here. So these balls, and of course, everything is in 2 dimensions over here. So we're just going to call them balls. There are the pegs, basically immovable balls. We can call them immovable balls. All right. And then there are these buckets into which these balls will collect into. All right. So we basically need to design 3 objects. And that's what I have done for my setup today. All right. So let's just go through the setup. So I have the HTML page, which basically has the canvas. Now the canvas is a little bit different. As in I have a canvas over here. I am pretty sure that the camera is All right, so I'm just going to shift this just by a little bit. Hold on, do I have, okay, let's just take it from last week's episode. Just going to do this little bit of setup. I'm not sure if I'm going to, all right, so this, I opened the wrong project. All right, let's open Newton's Cradle. I'm definitely going to have to edit this out. All right, just going to place this over here. All right, so why do I need to place this? Just so that I can have this right in the center. So what do I have for setup over here? So I have a canvas, and on the canvas I have a few balls flying. So that's all I have for setup. Let's look at the different classes that I have. I mean, first things first, I have the main JavaScript file where I have the init. I have the resize canvas. The canvas element, I get the width, height. I already have the animate function already built in. Then I have the ball class. What does the ball class have? So it has two main properties that it has are the location and the velocity. They are both point objects. All right. I have a function called add force. Now, if I specify a force over here, that gets added to the velocity. I have an update function where the velocity is added to the location. All right. I also have a couple of functions called the check canvas bounds and the check speed. All right. That you already know what this check canvas bounds is capable of doing just by the name itself. It will just ensure that the balls remain within the bounds of the canvas. And what will happen is that, we'll just take one case over here. If the ball flies or tries to fly outside of the bounds on the right hand side of the canvas, then its velocity, so over here I'm basically making the x velocity or the x component of the velocity as negative. All right, but I have this constant over here called coefficient of restitution. What does that mean? It means that every time the ball actually collides into the object or into the wall, it loses some energy. That loss is basically coefficient of restitution, and in my collision test I have essentially declared it as 0.8. So every time there is a collision, it will lose about 20% of its energy. All right. That's one. So that's the check canvas bounds. The other one is the check speed. Now, what I want to do is to ensure that we have something called as the terminal velocity for all of these balls. All right. So this is essentially terminal velocity, where let's just assume that there is some kind of air resistance or something like that. So if the velocity in either direction or the x or y direction exceeds a predetermined maximum speed, then we just restrict it to a maximum speed. In our case, I have restricted the maximum speed to 8. So basically each ball cannot move more than 8 pixels. All right. And then there is a render function where the ball is essentially responsible for rendering itself onto a context. All right. We've already seen this in our previous episodes. All right. Another thing that I have done is I have introduced a bunch of constants in the code space API, and this is what the constants looks like. All right. So I have 3 constants for now. I have the 2 pi, half pi, and radians, which I think we are going to be needing it over and over again, which is why I've like predetermined, pre-declared them over here. So remember, whenever you're drawing an arc, a full circle is essentially 2 pi. So if you do maths.pi into 2 each and every time this thing is rendered, then it's a bit of calculation that you need to essentially take care of, which is why I just think it is good to have it pre-calculated and everything. All right. So that being said, so that's just the ball class. What do I have next? Next, I have the peg class that should represent the peg over here. Each peg has a location and it has a radius, and then it has a render function. Basically, it just renders on the screen. And the third thing I have is the bucket class. I'm calling it the bucket. All right. So essentially a bucket is nothing but a rectangle. We'll just see how to sort of simulate it on the screen, because the bucket is open from the top and everything. It's not just a rectangle. And then it has an X, Y, width and height. And then I have the render function that essentially renders it on the screen. All right. So what do I have? So all that being said, what have I done? So I have this thing called numballs. All right. I mean, basically the I have this constant called as the number of balls. So which is basically 20 over here. And, I just create them randomly across the screen. And then I have a ball is equal to, I just give it a random point, give it a specific radius, and then I add them to the array. And then I animate them over here. What am I animating? In the animation function, I have this function called add force, which is basically nothing but gravity. All right. I mean, I'm basically adding the gravity force over here. Remember that gravity is a constant. It's a constant force. It keeps on getting added in such a way that basically these balls will start to accelerate, but then they'll meet this terminal velocity and all of those things. So every time this animate happens, I add a gravitational force. I perform an update, which basically updates their location, and then I perform a render. When all of this is put together, this is what it looks like. All right, all of these things, all of the balls, they basically fall down. But you'll immediately see that there is something wrong over here. What is wrong? I mean, basically these balls are just going into each other. They don't collide with each other, and that's where we need to perform collision. So we need to do two things. Number one, we need to do collision detection, and we need to do collision resolution. Collision resolution obviously is like the most difficult part of it, or is the most tedious part of this process. But I have a paper over here. This is the same paper that we visited last week when we wanted to do the simple when we wanted to do the Newton's cradle, and we were doing this conservation of momentum and conservation of kinetic energy and all of those things. All right. But this time we are going to be doing this in 2 dimensions. All right. Elastic collisions in 2 dimensions. And this is essentially a 7-step process through which you can perform this one. So we'll just read through the paper and we'll do the collision together. All right. So number one, when we talk about creation, so the number one change that we need to do over here is that, okay, so first things first, all of these balls are essentially created at the exact same time. We don't want to do that. What we want to do is to have them sort of drop through the spout over here. So let's say if this is the spout, they drop more or less one by one or in a specific order, right? So we'll fix that first. So that's the number of balls. All right. I already have a variable called as the ball counter over here, and I'm going to be creating them in the animate function so that in the manner that they sort of start falling from the top. All right. So how am I going to do this? I'm going to say if B counter is less than num balls, then go ahead and create it. But don't create it like, at a random location. You always want it to be created at the very top of the canvas, one after the other, right? I'm also going to say ball counter plus plus. All right. So X shouldn't be this. X should instead be somewhere in the middle of the screen. I'm going to say width by 2, and I'm also going to say minus random between minus 10. Okay, minus ball radius and ball radius, so that they don't fall all directly in the center. I'm going to say start falling anywhere within a specific point in the middle of the screen, start falling. So now I have the X. Y, what should Y be? They should not all start from the same Y location, or maybe they can. But for now, I'm just going to say start from off the screen and start at, let's say, minus 50. Now let's see what happens. All right. That being said, I do not need this. Why don't I need this? Because I'm going to be creating these balls inside of the animate function. Width. What did I do wrong? Again, there is a problem. What is the problem? They're all created at the exact same time, or they're created like so fast that, you know, there's not going to be in our collision detection is going to be messed up. All right. So I have a solution for that. I already have a variable declared here called counter. All right. So I'm going to be using this, and I'll say if counter modulo 15 arbitrarily, this is just arbitrarily, is double equal to 0, only then you create a new ball. And I'll say counter plus plus, it doesn't matter. All right. So now what happens? So only one got created. So that's counter plus plus, counter modulo counter plus plus. So this should essentially be created each and every time, correct? I'm just going to look up something. Oh, you know what? I'm only incrementing this out. This should be outside of the loop. All right. So there you go. So that's how, okay. So that is still, okay. Okay. So now I like how they are generated, but let me just put this as 5 and yes. So this is more like it. All right. So now I have this one. So, but the one thing that I don't have is the collision between these two balls. All right. Or collision between balls. Just so that we are able to see the collision properly, I'm just going to say the number of balls is just 2. Why just 2? Because this will allow me to see the collision between these two balls more properly. I'm also going to be increasing their radius. Let me make them 30. So that would be like, 60 in diameter, but that's fine. Now I need to make sure that this is 10 so that they are created a little bit separate to each other. So this will allow us to basically see what's happening. All right. Beautiful. So now I have the balls and I have this one. Now I'll create a function and I'm going to call this collide ball. Basically two of these things will collide. I'm just going to say collide PB, for ball. And this will accept two of these ball parameters. And what will essentially happen is that we will need to calculate the collision between the two. Let's just reference the paper back. Find the unit normal and the unit tangent vectors. The unit normal is a vector which has a magnitude of 1 and a direction that is normal to the surfaces of the objects at the point of collision. All right. So this is the unit normal, which is basically perpendicular to wherever they collide, and unit tangent is essentially parallel to where they collide. The unit tangent is a vector which is tangent to the circles. I said parallel, but I meant tangent, which is tangent to the circles surfaces at the point of collision. All right. So that's the unit tangent. It also has the statement saying magnitude of 1. What does that mean? It essentially it's like a percentage, right? If I said my marks in English was 25 out of 55, that doesn't make any sense. Your natural question would be, how much percentage did you get? How much out of 100 did you score? All right, so that's what it is saying. So these unit normals and unit vectors, when you unit tangent, when you calculate them, they would arbitrarily give you some value, but you need to sort of give them a magnitude of 1. Basically saying between 0 and 1, how much would they be? Or essentially saying, give me a percentage of 1, or if that makes sense. All right. First, calculate the normal vector. This is by taking a vector whose components are the differences between the coordinates of the centers. Let x1, x2, y1 and y2 be the x and y coordinates of the center of the circles. Then the normal vector n is equal to x2 minus x1 and then y2 minus y1. So this is essentially just an object that contains both of this. So let's just do that. So before we do that, what we'll do is that to calculate all of this, we would need all of these variables, right? x1, x2, y1, y2, and all of those things we will need. So we'll just declare those variables ahead of time. So let's just write that. Okay, so I'm going to say let x1 is equal to x2 is y All right, so that's the x1 and y1. I'm just going to, oh, I'm sorry, this is y1. I'm sorry. This is x2 and this is y2. So now I have the coordinates of these balls. I'll also need the mass of these balls. Yes. So whenever you are calculating this, you would also need the mass, because if you look at the ultimate formula, you will see that we require the mass of these balls. Now here's the thing: all of these pegs, if you look at the Galton's board once again, they look like they're all the same mass, or more or less the same mass, and that's what we're going to do. We're going to create them as I don't know, arbitrarily 20 I'm just going to give. All right, so ball mass. So M2 is also ball mass. All right, so I'm just going to have all of the variables ready. Another thing that I need to do is get their velocities also. So I'm going to declare those variables also. A ball dot velocity dot x v y1. So that's the velocity in the y direction p and b. So this is vx2 and vy2. So now I have all of the variables that are required to perform the calculation. Let's look at step 1. What does step 1 say? First, find the normal vector. This is by taking all right, this is by taking the difference between, so basically normal is x2 minus x1, y2 minus y1. That's all. Now this paper over here suggests that you make a point. I mean, that'll only complicate things. So I'm going to, okay, say step 1, xn or the xn is equal to x2 minus x1 and yn is equal to y2 minus y1. All right, so now we have the normal. Next, find the unit vector n, which we will call un, and this is done by dividing by the magnitude of n. So therefore the magnitude or the unit normal is n by the unit normal in the x direction squared plus the unit normal in the y direction squared. All right, so now we have this and this. So what is magnitude? So basically this is magnitude, and what is magnitude? It is nothing but math dot square root of x in the normal direction plus y in the normal direction and y in the normal direction. All right, so that's the magnitude. And what is the unit normal? All right, so sorry about that. So let x unit normal or unit normal in the x direction is equal to the x normal divided by the magnitude, and the same goes for the y. So y in the unit normal is y normal divided by the magnitude. All right, so there is a pitfall over here. What is that pitfall? Because we are doing a division over here, it might just so be possible that the magnitude results in a 0, especially if they are, it is possible that they are 0, especially if these two result in 0. And so just so that we are safe, you say if magnitude is not equal to 0, only then you do this, or else let them both be 0, right? Let this be 0, let this be 0. If magnitude is not 0, then you set these values up. All right. What is he saying? Okay, next we need to get the unit tangent vector. This is easy to find from the unit normal vector. Just make the x component of the unit tangent vector equal to the negative of the y component of the unit normal vector, and make the y component of the unit tangent vector equal to the x component of the unit normal vector. So basically what he's saying is that you just say let x unit tangent vector is equal to negative y negative of this, and the y the y unit vector is basically positive of this. That's all. So basically what he's saying is that, you just assign it like this. So now that's essentially step 1. Step 2, create the initial velocity vectors v1 and v2. These are just the x and y components of the velocities put into vectors. All right, that's fine. We already have the vector. I think we have already done it. So this is, so that's essentially it. So we don't need to do step 2. That's already done. Step 2 is done. Next, let's just go to step 3. What's step 3? Keep in mind that after the collision, the tangential component of the velocities is unchanged, and the normal component of the velocities can be found using the one-dimensional collision formula presented earlier, or basically last week. So we need to resolve the velocity vectors v1 and v2 into normal and tangential components. To do this, project the velocity vectors into the unit normal and the unit tangent vectors by computing the dot product. All right. So what do we need to do? So velocity 1, so v1 in the normal is unit normal dot product v1. All right. I think, so a dot product, all right, so what is a dot product? A dot product is essentially nothing but, so let's say you have a point object which has two variables, x and y. So a dot product is essentially nothing but the x components multiplied together plus the y components multiplied together. That's all a dot product essentially is. So we need to have these 4 variables, so which is the normal, tangent, normal, and then tangent. All right. So we need to basically calculate these 4 objects. Step 3 is let v1n is equal to the unit normal into v1. Okay. What is the unit normal? So this is the x unit 1 into the v1, so which is vx1, plus the y unit normal into the y unit normal. So this is the y unit normal multiplied by vx1. That's how you calculate the velocity norm, the velocities in the normal tangent. All right, let's just say, what is that? So that is v2. So v2n is nothing but this is 2. That's all. And then we'll calculate the tangential vectors also. So what is that? So that is t, and that is t, and this is nothing but multiply this by c. I hope in all of these copy pastes, I'm not making any mistakes. So that's essentially step 3. All right, what do I have next? Let's see. Step 4, find the tangential velocities after the collision. This is the simplest step of all. The tangential components of the velocities do not change after the collision. And because there are no force between the circles in the tangential direction during the collision, so the new tangential velocity, so the new tangential velocities are simply equal to the old one. All right. So what are we doing over here? So this is step 4. This is where we start to essentially compute the resultant velocities after the collision has happened. So what are we doing here? We are essentially saying, let's find the collisions after the, let's find the velocities after the collisions has happened. So let's say, so let v1 t prime. What is that? So you see this accent over here? So that's essentially prime, which means it's after the collision has happened. So for the tangential velocities, because the velocities do not change after the collisions, and because there's no force between the circles in the tangential direction. All right. So what this essentially means, or what I think it means, is that when these circles collide, I do not have sort of a frictional force between them, because this is like a perfectly elastic collision. So I think in general you need to worry about friction between these two, because I think there would be velocities in the tangential directions also, because that's how billiards balls work, right? you're able to hit it or give it a specific spin and all of those things. So anyways, in this case, we are not calculating tangential velocities, which is why the velocities after the collisions in the tangential direction, we're just saying, is essentially equal to this. That's all this ever was. Step 5 is the most important step of all, where we use the formula that we saw last week, and we'll calculate this one. So we just essentially have to like copy this and we'll have to put it. All right. So what is this? So this is, so velocity in the normal direction, or let v1n prime is equal to the v1n into m1 minus m2. All right, so which is the velocity into m1 minus m2 plus 2 into, I'm sorry, I'm switching between these two windows so quickly. Maybe I should just put this over here. I do not need this to any. How do I close this? Never mind. Maybe I put this over here and then make it difficult for you to read or follow what I'm doing. But essentially, all right. So I have this 2 into m2 into v2n. All right. So I have that. I'm just going. Do I need? All right. Divided by m1 plus m2, divided by the masses of the two balls. All right, so that's v1 prime. All right, so that's v1 prime, or the velocity in the or the normal velocities after the collision has happened. v2 prime would actually be exactly the same, except it's m2 minus m1. Except it's m2 minus m1 into 2 into m1 minus m. No, okay, so this is v2n and then m1 plus m2. So now I have the primes. Yeah, that's it. I mean, primes meaning I have the velocities after the collision has happened. Perfect. I think, yeah, that's about it. Convert the scalar normal and tangential velocities into vectors. This is just easy. Multiply the unit normal vector by the scalar normal. Yeah, so basically a reverse of the process needs to happen. All right. So what does that mean? So I basically have the velocity, so I can just say a ball dot velocity dot x is equal to v1 prime into x in the normal direction, correct? Into x unit n. So yeah, so that's what they're saying. So v1 prime is equal to v1 prime is equal to the so this is the velocity. So you take the scalar and then take the unit normal multiplied by x unit n. So that would be my velocity after this has happened. And this is, oh yeah, so the velocity is unit normal prime plus unit tangent prime. So I have to like sort of add them, and I'm just going to put them in the same equation. All right, so this is so what is okay, so this is, yeah, so this is v1 t prime into I'm really hoping that you are all with me on this one, into the unit tangent direction, into the unit, so that is unit x unit t. All right, so that's the velocity in the x direction. So that is actually I'm just going to verify if this is correct. All right, and in the y direction it would be v2 prime. No, it would still be this, but this would change, where I'm going to say this is the y unit 1, v1 prime into the y unit in the tangent direction. So I have both of these over here. So that's the velocity of the first ball. For the second ball, I'm just going to mark this step 6. For the second ball, it's the exact same thing, but this is V2 prime, V2 tangential prime, and the same thing goes over here, V2 n prime and V2 n prime as well. All right, just going to look at this for just 1 second and ensure that this is correct. All right. All right, I think we are good. All right, so now I have this collide. We'll find out if this is correct or not. All right. So let's see. So once again, I'm just going to copy this instead of. So remember, we need the collision between these two balls. All right. So I'm just going to create a separate loop so that my rendering loop is different from the collision loop. All right. All of the balls need to collide with each other. So I'm just going to call this J. All right. If I is equal to J, I mean, we don't want this. We don't want this ball to collide with itself. I'm beginning to think that this word ball is not the. I mean, I shouldn't have used the word balls, but whatever. We'll continue. All right. So anyway, we basically don't want the ball to collide with itself. All right, so collide VB over here is a resolution function. All right, this function doesn't determine if the two balls have collided. It only resolves if the two balls have collided. I need to first of all find out if they have collided, and that's actually pretty easy. So I can just say let distance between the two balls would be get distance between balls of I dot location dot x comma balls of I dot location dot y say balls of j. All right, so this essentially uses the hypotenuse function to do it. All right, find the distance. Let check radius or the radius or the total of the radiuses. Balls of I plus dot radius plus balls of j plus radius. So I have the two radiuses. If distance is less than or equal to check radius, a collision has happened. All right. How do I know a collision has happened? So basically we are calculating the distance between the centers of these two balls over here. If the distance between the centers is less than the sum of their radiuses, then I know that a collision has happened. All right. That's what we are checking over here. If it is less than that, then I can just I can just say perform a collision between these two balls. That's all. Let's see if this works. You see. So now there is a problem over here. What is the problem here? Maybe I'm not doing my calculation correctly. So I did find out what the issue was. It's just that I was performing a wrong calculation at the velocity 2 tangent. I mean, I think I was using the y unit tangent instead of the x unit tangent. So that's corrected. But there is another issue that we need to talk about. The thing is, how do we detect collision? So collision detection itself is like a very vast subject. Here we are using a very simple method to do it. There is something called as a priori collision detection, and then there is this normal kind of collision detection that happens. A priori collision detection means you find out ahead of time where a specific ball would be on the screen. All right. So let's say you determine that at time t we are going to collide. Then you increase the timing counter on your computer and see if this time matches the time at which the velocity the collision was supposed to have happened. Then the collision has happened. That I believe is called a priori collision detection. Now we are not going to go up to that extent over here. Instead, we are going to use a couple of cheats, a couple of shortcuts to help us perform this collision detection in a semi-neat manner. All right. What do I mean by that? So over here, instead of doing the get distance, I mean, remember I was doing the get distance with just the locations. The only change I have made is I have added the velocities to the locations and then I'm doing the get distance over here. So this is sort of pseudo a priori. So this isn't a priori, this is pseudo a priori. So this will give me one step ahead of time as to when the collision would happen. So in this case, I'm just, after I have added the velocities and I have, I have the distance checked. If the distance, if the balls have collided, then the collision has happened. So now if I check at, I've increased the number of balls also to 20, you will see that this looks very true to the physics of it. But as soon as all of the balls have started, have sort of settled down, you will see that there is a problem. They sort of go inside each other because remember, so this is the problem with not having discrete mathematics. So essentially what is happening over here is that we have a situation where sorry, I keep switching between this and that. I'm sorry about that. All right, so anyway, so that's done. So essentially what happens is that because gravity is like a constant force, it never ends. That's why we have these balls that eventually go inside each other. There is a shortcut, or there is a way to actually get around that. How do I get around that? So I have another website over here that specifically mentions this sticky problem. If you run, so let's just read through the website. If you run through the simulation now, you'll find that the particles stick to one another exactly as how it is happening over here, and can even get stuck mid-air. So yes, so this is something that can definitely happen. All right. To avoid this problem, we add some code to the collide function to fudge the fact that the particles should have bounced before they overlapped. So there is a very simple formula given over here. So we're just going to take this formula and we're going to apply it when the collision happens. All right. So let's just basically copy this, and right when it happens, we'll right when the collision happens, we will put this. So what does angle mean over here? So angle is obviously a variable, which is basically half of math.pi plus tangent. What is the tangent? So over here they are calculating the tangents or the a tan 2 variable or value between the two balls, and that's actually quite easy to do. So I can just say let tangent is equal to math.a tan 2 of actually usually we give dx comma dy. Dx would be the x2 minus x1 and dy would be y2 minus y1. So I can just do that, right? So that would be, oh no, it's not x2 minus x1. I mean, because I'm adding the velocities over here, so I can't actually use that. So I'm just going to say, yeah. So it's just this minus this comma the y positions now. So yes, so that's this minus the y, so the y component. So now I have the tangent over here. So I'm going to say let angle is equal to 0.5 into math into pi. Remember, we already have this pre-calculated, so I think I can just say constants dot half pi, is it called? I can just say half pi plus tangent. Yeah, so I can just say constants dot half pi plus tangent. Would that all be it? So what is tangent over here? Let me just take a look at it. Yeah, so there it is. So tangent is math.a tan 2 dy and dx. So that should be dy and then dx. So I just want to make sure that I have all of the array axes proper. So let angle is equal to constants. Yes, and of course I'll have to sort of say dot location dot x is equal to what is that, math dot sine into the angle. And this is plus equal to, so we're going to say plus equal to the same goes for the y, and this is minus equal to math dot cos of angle. And I'm just going to give a little gap over here, and the same thing goes for the other ball also. So this is nothing but j of x minus equal to sine. So basically what we are doing here is we are taking these. So if the collision has happened, if the distance between them has like sort of gone, if they have like gone inside of each other, we're just placing them right outside so that it looks as if they haven't gone into each other. So this is once again like a cheat that we are using to ensure that it looks proper to the physics of it. All right. Before we proceed, I just want to make sure that we are indeed using the proper constant. So this is constants dot half pi, which is math dot pi by half. So we already are using, okay. So we are doing this. Now I think I need to like sort of convert this into radians. So I'm going to divide this by 180. So half pi by 180 plus the tangent would give me the angle, and then I do this one. So this should at least prevent these balls from going inside of each other. All right, so pi is not defined. Oh, I'm sorry, it's half pi. All right. So yes, so this should in fact prevent it from going inside of each other, but eventually, because our physics doesn't use very, very discrete mathematics, you'll see that weird things like this start to happen. But I'm telling you right now that this won't be important as far as creating the Galton's board itself or simulating the Galton's board itself is concerned. All I want to make sure is that to some extent this remains correct. All right. So that being done, we have now simulated the balls. Let's draw the pegs on the screen. All right. So all right. So we have the animate. So remember, we don't have to create the pegs and the animate function. We can create them beforehand. So let's just go ahead and create the constants that are required for that. Say peg. I'm going to say num pegs. How many pegs do we need? All right. So once again, going back to our image over here. So that I placed it on my desktop, and I'm going to see how many pegs do I need to do this. So you can see how the pegs are actually drawn over here. So there is some number of pegs at the top, some number of pegs, row by row, there are like different number of pegs. And that's exactly what I'm going to do. I'm going to make sure that there are different number of pegs at different number of rows. Okay. So how many number of pegs are there in each row? I'm going to say, let's say 17 pegs in each row. All right. Let's say there are 17 pegs in each row, and each of these pegs will also have a specific radius. So I'm going to take this. So peg radius, I'm going to make it, let's say 10. Yeah. And by the way, I'm also going to reduce the radius of the balls. Let's make them 10. Yeah. So peg radius, let me make them, let's say for 15 for now. I'm going to leave them as 15 for now. All of these pegs need to essentially start from a specific location on the screen. So that's what I'm going to do. I'm going to say let start y is equal to 50. Basically, I'm starting arbitrarily from, let's say, 50 pixels from the top of the screen. All right. Let's say I'm just going to have a variable over here called counter. And what I'm going to use this for is that, so the number of pegs on each line would be like 17. However, there are going to be like alternating number of pegs on each line. So I'm just going to say 17, 16, 17, 16, 17, 16. So, and depending on what this counter is, I'll have either 17 or I'll have 16 pegs. So what the effect that will have, So what will happen is that because I'm going to be placing these pegs right at the center of the screen, all of these 17, they're going to sort of try to adjust themselves. So they will sort of appear alternating, not much different from the image that I was showing. So not much different from, let's say, over this. So you can see that each alternate row is sort of offset from each other so that the balls that are falling, fall into a specific peg or collide into a peg every now and then. So that needs to happen. Okay, so all right. So for that, I'm going to have that. So each peg also needs to have a specific gap between them. All right, so I'm just going to say for now that this gap is going to be 30. All right, this is also once again arbitrarily chosen. All right, so how many rows of these pegs do we need? All right, so how many rows of these pegs do we need? Can we have like, let's start with 6 rows. All right, so for let I is equal to 0, I less than 6, I plus. All right, so I'm going to have 6 rows of these pegs. Okay. What is the peg count? The peg count is nothing but the number of pegs. However, if counter divided by 2 is equal to 0, if it is an even number, then have, let's say, the number of pegs, or have number of pegs minus 1. All right. All of these pegs basically need to start from a specific location. Where do I start this from? The center of the screen, of course. So that would be width by 2 minus the number of pegs into the radius of into the peg radius plus the gap between these pegs. All right, does that sound right? Yeah, and this divided by 2. So that's where it should essentially start from. So that should be the so that should be where they start from. I'm just going to go ahead and put this thing over here. Hold on, no, I think I'm getting it wrong. So this should be multiplied by peg. Yes. So there you go. So that is my start. So let's say so that is my start x. Let j equal to 0, j less than peg count, j plus plus. Okay. A peg is equal to new peg. What do I need for this peg? A location, and then I'm going to need a radius. Location is nothing but a point, so I'm going to say new point of start x comma start y, and then a radius which is nothing but peg radius. So I now have a new peg. Add this to an array of pegs. All right. So I've added them to an array of pegs. Once I have added them, I need to increment the start x. Start x plus is equal to, so that should be plus equal to the gap plus the peg radius. All right. So that's the, so I need to increment the start so that each peg appears that many positions after the peg. So I have that. And every time a row is complete, I need to say start y plus is equal to gap. All right, so I'm putting a gap between these two rows. Do I need to add the peg radius over here? Yes, let's just add the peg radius here at the start y also. So now I have all the pegs initialized. All I need to do is like sort of render them. So let me render them here for let I is equal to 0, I less than, I don't know how many pegs there really are, and then I plus plus. All I need to do is say pegs of I dot render of context. That's it. Okay, let's see. Oh, there you go. I do believe these pegs are a little bit big, and they're not easily meshing with each other. Are there too many pegs? Let me put the number of pegs as, let's say, 10. Oh, there are always 10 pegs. How come? I did say, oh, you know what? I'm not incrementing counter over here. So I can say counter plus plus. So now there is always an even and odd number of pegs over here. Let me actually go ahead and set this back to, you know what? I think the gap might not just be, it might not be enough for the balls to actually, no, let's leave it at that. Let's leave it at that. What am I missing? Yes, I'm going to set this back at 17, which is arbitrary, just so that they can like fill the entire screen. So there you go. So that's the pegs that have been created. All right. Another thing that I need to do is create those buckets where these balls would go ahead and fall into. Okay. But before we do that, I'm going to reduce the ball radius, let's say 7, so that they look appropriate. All right. I really hope this renders properly on the screen and everything. And just going to change something over here. Yeah. All right. So this looks more appropriate and everything. That doesn't matter. And then I can have the balls sort of like falling. There's also another thing that I'd like to do. So this Y gap, I do believe it needs to be a little bit bigger, but that's okay. We'll get to it when we get to it. All right. So now that we have the pegs drawn on the screen, let's create the collision between the balls and the pegs. All right. Pegs are nothing but a version of the balls themselves. I mean, they also are balls, but the only difference between a ball and a peg is that a ball is movable and a peg is not. All right. So that makes things a little bit easier for us. First of all, let's create the collision between the ball and the peg. And so we go to our loop where we are calculating for the ball and ball collision. And over here, inside the outer loop itself, let's create another loop. Let's say where, right? So that's J. I'm going to use K over here. So JKL, right? So I'm going to say K is equal to 0, K less than pegs dot length, K plus plus. So we are using the variable K to determine the pegs. I mean, I don't want to use the same variable J over here. Maybe I can, but I'm just not going to do it. All right. So what do I, so I need the exact same. So even for collision detection, I'm going to use the exact same formula. All right. All right. So I'm just going to use the exact same thing. All right. So this is balls of I dot location. X2 is equal to pegs, right? Pegs of K dot location dot X. And remember, a peg has no velocity. So I'm going to remove the velocity calculation from there. Y2 would be location dot Y. And the same goes for the Y. Get the distance, get the check radius. If a collision has happened, I do calculate the tangent. And for the tangent, I'm going to use the pegs of J dot location. So that would be pegs. I'm sorry, pegs of K. I'm sorry, that should be K. So this is balls of I. I'm sorry. Oh, I'm sorry. This is balls of I, pegs of K. And then this should be once again balls of I. Sorry about the confusion. And pegs of K dot location dot X. So now I have that. I have the tangent. I need not change the pegs. So all I need to do is change the balls location. So balls of I dot location, and then I have the math dot sign and everything. All right, just making sure that we are correct over here. All right. Now, obviously, I cannot use the same function collide balls and balls, so I cannot use that. So I'm going to create another function, which is essentially just going to be the copy of the same function, except I'm going to be calling it collide a peg and a ball. Collide peg and ball. So that's the resolution function. So it would be a collision between a ball and a peg. All right. So x1, x2 would be a peg dot location. The same goes for the velocity as well. But remember, I'm actually not going to require a velocity over here. So the peg's velocity would essentially be 0. All right. What is m1 and m2? All right. So now I have the location of a ball, the velocity of a ball, and the velocity of a peg, of course. The mass of the ball would be the ball mass, but the mass of the peg would essentially be infinite. Because it's like it remains fixed for all intents and purposes, it's going to be infinite. And to do that, I'm going to use the number dot max safe integer, which basically means it's like a very high number. The peg is going to be immovable. All right. Everything else remains the same. Everything else remains the same. We do not have to change the velocity of the peg itself. So we need not calculate or reassign the velocity of the other component. So we do not need that. Now, because we don't need that, we don't need this prime calculation, and we also don't need this variable at all. Now, if we don't need this variable, I mean, the IDE essentially states that I don't need this variable as such. So that should determine the collision between a peg and a ball. And if I'm not wrong, this should essentially work. Oh, hold on. Is that at the wrong position? Yes, it is. All right. So, yes. So now I have the pegs and then a collision between the peg and the ball. Let's see if that actually works. J is not defined, of course, because I would have used J somewhere. Yeah, there it is. So that's K. So that is peg of K dot radius. So that's the peg radius that I have to take. Anything else that is using a J? I don't think so. Let's see at line number 82. What am I doing at line number 82? So that's a ball. So that's the balls of iron. That's pegs. I'm sorry. 92. Oh, of course. I'll have to say peg. I'm sorry. So there you go. So that actually they're just not falling inside, and the reason for that is because these balls are a little bit too big, and then there is some stickening happening over here, but that's fine, I guess. This is why I was stating that okay, so we essentially need to do two things over here. Number one, we need to increase the Y gap between the two pegs. Remember when we initialized it, we did not leave any extra gaps. I'm just going to say arbitrarily, I'm just going to say make sure that this is 10. Add 10 to each the Y gap. So that happens. So that looks okay. I mean, in my opinion, that's number one. Number two, let's reduce the radius of the ball. I'm just going to say, make sure it is 6. I think that should do it. That's number two. The third thing that we need to do is that, remember, these are like, perfectly, what do you say? These are perfectly elastic collisions, but that's not how it is supposed to be, right? So what I'm going to do is I'm going to say, so after the V1 prime, so after the normal, after the velocity in the normal direction is calculated, I'm just going to multiply it by the coefficient of restitution. And what that should do is every time there is a collision, every time there is a collision, it will basically reduce the. So I have this. I have this. Do I have to do it for the V1 prime as well? No. Okay. So yeah. So now now that I have done that, so what should happen is that there should be some dampening of forces that happens over here, and that dampening, sort of seems to fix the issue with them bouncing all around and everything. And you can see that the pegs do fall to the bottom as if they were, as if this physics was real or something, but this is just simulated. All right. I think an increase in the coefficient restitution should make them fall faster or something. But for now, what I'll do is let me just try and increase the gravity over here, double the gravity here, and see if this makes things a little bit faster. So there you go. So that does actually make things a little bit faster. Another thing that I need to change is, do I need to reduce the gap or increase the gap? You know what, for now, I'll just leave it like this. All right, now that we have created the balls, the pegs and the collisions between them, it is time to now move on to the buckets. All right, so let's look at this diagram or this photo once again. You will see that the number of buckets is more or less equal to the number of pegs that we have. And the peg and the buckets, essentially the dividers of the buckets at least start from exactly where the pegs is. So we need to sort of do this as well. All right. And the buckets essentially serve as a reservoir for all the balls that are falling. So yeah, so we'll need to essentially do that as well. So let's do that. So I'm going to create a variable here called, buckets, which is also an array. I'm just going to push them into. So remember how I was saying that the number of buckets is more or less the same as the number of pegs. So I'm just going to say, I'm going to create a variable called numBuckets is equal to more or less equal to the number of pegs. All right. Now each bucket has a certain width. So if you look at this, I mean, it has a certain width. What is that width? I mean, I think over here it would be the radius of the peg itself plus the gap that we left between each of the between each of the pegs. So I'm just going to do that, right? So say bucket width would be the peg radius plus the gap that we arbitrarily assigned over here. So I have that. So I'm going to need, so I'm going to have, let's say 17 buckets, and they need to sort of start from somewhere, correct? So how do I, so I need a start X and a start Y. So I'm going to say start X is equal to, now I'm not worried about using the let over here because the start was declared within this block. So I'm okay with declaring the start X. And yeah, so that would essentially be width by 2 minus minus the number of buckets into the bucket width. All right. Do they need a gap? No, they don't have a gap. So I don't need this by 2. So that would be where they are starting from. Start Y would be, so I need these buckets to essentially reach right at the top over here. So I'm going to need that start Y. So this is where they have started, and this is where they have, so this is where the pegs have started, and this is where the pegs have ended. So that would be, wherever these pegs have essentially ended. So that would be height minus start Y. So so the buckets would have to essentially start from over here. So let me just yeah, should this be bucket height or so that should be the bucket height. Yeah. So the start Y. So where should they start from? So they should essentially start from here. And yes. So the bucket height, I mean, because we do need a height, should be, let's say, start Y. So which is basically where these pegs ended. I'm going to say plus, say 20. All right, arbitrarily. I'm just going to start this arbitrarily. And where would they start from? I'm sorry, their start Y would be, yeah, there it is. I'm sorry, I've already declared it. So it would be height minus the bucket height. All right, let's see. So for let I is equal to 0, I less than num buckets, I plus plus. So I have that going on. Variable bucket is equal to new bucket of, it needs an X. I have a start X, start Y. I have a bucket width, and I have a bucket height. All right, so and then I'm going to say buckets dot add. I'm sorry, buckets dot push a bucket. Once I have done that, I also need to increment the start x. So I'll say start x plus is equal to bucket width, so that they appear one after the other. So I have that created. Let's see if I can draw them. So I have the pegs, I have the balls that are rendered. So I have, so the pegs, then there are the balls, and then let's say there are the buckets. All I have to do is say pegs of I dot render of, give it a context. That's about it. All right. I think that's all is required to do this. Of course, there is an error. It has already been declared. Init is not defined on onload. Come on. Yeah, so I don't need to declare start y once again. I'm probably missing a bracket from somewhere, which is why it says that the init was not, numBuckets is not defined. I'm sorry. This should be. All right, so there you go. So now we have the buckets simulated. So now what is my intention with them? So the idea is that these balls would fall into these buckets, and now they need to like sort of remain within the bounds of the bucket where they are falling in. And that's once again another physical calculation that we can probably do at some other time. Now the thing is, in the interest of time, I'm going to use a shortcut. What I'll do is that every time a ball enters a bucket, I'm going to raise its flag, or I'm going to say you are this bucket is filled by this many degrees, or sorry, this much amount, and that would sort of have an indicator as to how much that bucket is full by. So that's my intention over here. So let's just get on that. All right. So we have created the buckets and everything. I've created a variable over here called fill h. All right, basically means fill height. It essentially says, or it means to say how much this bucket is full by. So if a ball essentially enters into a bucket, we would increment this so that we determine, or we show its fill status, or how much it is full by. So all we need to do is say a context dot fill style is equal to, we'll give it the same color here. A context dot begin path, a context dot rectangle, this dot x plus 1. I don't want it to like sort of occupy the entire rectangle or the entire bucket. Instead, I'll say I'll just give like a 1 pixel gap so that it probably looks neater also. This dot y plus this dot h minus this dot fill height, comma this dot width minus 1. And how much height should I give it? I should say this dot fill height. I think that should essentially do it. So what will happen is that if the value of this fill height is, let's say 30, then we would have like an inner rectangle. We just put the fill statement. So we would have an inner rectangle that would essentially fill it by that much. So now let's say if I make this 20, let's see what that looks like. So there you go. So when these balls fall over here, we'll increment these, that fill h so that each bucket has its own height. All right, so that's the shortcut that I'm using over here. And why are we using the shortcut once again? It's because if these balls were to collide with buckets, we'll have to write, once again, physics equations for all of that, check for the bounds and everything. Yes, and of course, it's possible for us to do it, but we'll leave it for another day. In the interest of time, we'll use this shortcut. All right, so we have accounted for the collision between a ball and a peg, a ball and another ball, a ball and another ball, and now we need to account for a collision between a ball and a bucket. All right, or basically what happens when a ball enters into a bucket. All right, so now I already have this for loop placed over here. I'm going to say if balls of I dot location dot y plus the radius. I mean, if this ball, I'm going to say plus radius. All right, so because so if this was the center of the ball, that would be its radius. I need to make sure that as soon as it enters the bucket, it registers it as being entered. If it is greater than buckets of L dot X, so if it is greater than this one, greater than the X, oh, I'm sorry, that should be the Y. That should be the Y. So if it has entered from the top, and if it is in between the X coordinates of the ball, of the bucket. So if so balls of I dot location dot X plus radius is greater than the bucket's X location. If it is greater than or equal to the bucket's X location, and if the location, if the X position of the ball minus the radius, the ball's radius, is less than or equal to this bucket's X position plus buckets of L dot width, right? So if it is within the bounds of this bucket, then I know, then what I have to do is say buckets of L dot fill H plus is equal to, for now, let me say 20. So every time a ball enters into this bucket, we'll say increase your fill height by 20. So that should give us an indication as to how many balls have essentially gone. And we should also be able to see if it sort of, gives a binomial distribution. Whoa! Do you know what happened over here? So essentially what happens is when a ball enters into a bucket, it doesn't stop it from from entering other buckets. So we need a marker on the ball itself saying, if you've entered into a bucket, you don't have to do any kind of simulation anymore. So I'm going to create a flag inside this ball, and I'm going to call this is done. Say false. For now, I'll declare this as false. Remember, we don't have to simulate this ball if it is done. All right, so I'm going to say if not this dot done, only then you can check for the bounds and everything, or else just let it, or else don't simulate it at all. And then I can say, even for the render, I can say if not this dot done, is done, only then you render it on the screen, or else you don't even have to render it on the screen. All right, so I've introduced this flag called is done, and if this flag is set, I don't have to sort of simulate it at all. So if, I'm sorry, what was that? If this ball is not done, only then do this, and then over here set this to true. So what will happen is as soon as it enters one bucket, it's done. That ball is no longer going to do any sort of simulation at all. So let's see now what happens. So there you go. As soon as it enters one bucket, it will only increment the bucket height for that specific bucket or wherever it falls into. So that's one thing that we have already done. Are we done? I think we are about done over here. Now all I need to do is increase the number of balls to, let's say, 500 or so, and see if it reaches or if it creates that binomial distribution that we've been that the Galton's board is actually so famous for. All right, so the number of balls, you've set it to 200. Let's make it 300 balls and see what happens. All right. Do I need to speed up this animation in post? I'm not sure, but let's see. Let's see how the simulation goes. All right, you get the idea of what's happening with this. What's happening with this. I can't wait to actually upload it onto our site so that you can actually see this for yourself. Download the code. Have fun with changing some of the values over here. Make the balls fall a little bit faster. See if they behave better. You know what? The problem is I'm dropping these balls entirely too slow, and I'm incrementing this fill height entirely too fast. So I need to change that. All right, so that's 300. What else? So where are we dropping the? Oh, so yes, so I've put 20 over here. Let's make it, because the balls are small. Let's make it 5 so that they fall in a little bit faster. So that's number 1, and number 2 is let's increment this fill height not by 20 but by 5. Now let's see what happens. So there you go. So that's a little bit faster. So yeah, I'm going to let it run to the end, and I'll decide later. I mean, if this episode is too long, then I'll sort of do some speed adjustments in the video post recording this. So there you go. It already looks like it's going to be a proper binomial distribution, just like as you would expect from a Galton's board. So that's 200 balls that we just dropped through this. It's not exactly the same gravity as you expect from as you see on Earth or in other simulations, but you get the idea. You already see the binomial distribution happening with this one. All right, I think that's all I had to show for this week. And before I do that, I'll just I'll just run this simulation once again, just so that we have the pleasure of watching this Galton's board run once again. Hey, you want to know a nice trick I discovered some years ago? All right, so this clear rect. Right, we're basically clearing. All right. First things first. Let's see what happens if we don't clear the rect. You would see that it will create these traces and all of those things, right? I mean, basically, we're not clearing the entire canvas before painting it. There is a very nice thing that you can do. So you're basically clearing the rect so that you can clear the canvas before you draw on the next frame. There is something else you can do though. Say context dot fill style is equal to RGBA of 255, 255, 255, 1, right? I'm going to give an alpha of 1 for now. I'm going to say context dot rect 0, 0, width, height. Nothing has changed from the clear rect, right? I mean, it looks exactly like the clear rect function. So what have I changed over here? It should change nothing. However, if I change the alpha to, let's say, a value bit less than 1, let's say I change this to 0.2, for instance. Look at that. It automatically creates these beautiful trails. So that was this week's episode, the Galton's board, binomial distribution, collision detection, and collision resolution. All right, so this is like proper 2D collision resolution that we have learned this week. I really hope this was fun to watch and fun to learn. I hope you download the source code from GitHub and make use of it, make some changes to it, make it so that these buckets are properly able to hold the balls instead of just increasing the height and so on and so forth. Yes. So that was the episode for this week. Join us again next week for another episode. We'll do something fun. And I'm hoping that Ravi is back from Bangalore next week as well. All right. Thank you so much.